Guidonia Airfield, Rome, June 1943. Engineer Capo Filippo Zappata wiped the sweat from his brow as he walked around the aircraft, sitting under armed guard on the tarmac. The twin-boom American fighter gleamed in the Mediterranean sun, its aluminum, skin unmarred except for a few scratches from the emergency landing in Sardinia 3 days earlier. A navigation error had delivered this technological marvel into Italian hands. A Lockheed P-38’s Lightning, completely intact, with both engines still warm from the flight north. When Zappata first laid eyes on the P-38, his reaction mirrored that of every Italian pilot. It was ungainly, awkward, with twin booms flanking a central nacelle that violated every principle of elegant Italian design. His colleagues had already dubbed it Il Diavolo, the twin-tailed devil. But the nickname carried more mockery than fear. However, as Zappata began his methodical examination, the engineer who believed in numbers was about to confront an unthinkable truth. The P-38 wasn't ungainly, it was a prophecy, and its components were mathematical proof that Italy had already lost a war its leaders still believed they could win. Zappata, senior propulsion engineer at Regia Aeronautica, had spent 15 years designing and evaluating aircraft engines for Fiat, Alfa Romeo, and Isotta Fraschini. He had studied British Spitfires, Soviet Yaks, and German Messerschmitts. He thought he understood the state of aviation engineering in 1943. He was about to discover that he understood nothing. As his team of engineers approached the Lightning with their toolboxes and measuring instruments, Zappata couldn't shake a feeling of dread. The Americans had sent this machine across an ocean to fight in a war thousands of miles from home. That alone suggested an industrial capacity Italy could barely comprehend. But it was what lay beneath those engine cowlings that would reveal a truth so devastating it would haunt Italian aviation engineers for the remainder of the war. They weren't just behind, they were impossibly, irretrievably outmatched. The P-38 Lightning represented everything Italian aeronautical engineering was not. Where Italian fighters were elegant, lightweight designs that squeezed maximum performance from minimal resources, the Lightning was an American brute. Massive, complex, and powered by engine technology Italian factories couldn't begin to replicate. Zappata knew the specifications by reputation. Twin Allison V1710 engines, turbocharged counter-rotating propellers, tricycle landing gear. On paper, it seemed almost wasteful. 2 engines where one would suffice, unnecessary complexity, typical American excess. But Zappata was a scientist, and scientists don't trust reputation, they trust measurements. His team spent the first hour documenting the external dimensions. The Lightning's wingspan stretched 52 feet, reasonable for a fighter. But the weight? When they calculated the loaded weight based on structural analysis and fuel capacity, the numbers were staggering. Nearly 18,000 pounds fully loaded, almost twice the weight of Italy's frontline fighters, the Machi C-202 and Fiat G55. How does something this heavy even fly? His assistant Giorgio Mancini muttered as he recorded the measurements. That's what we're about to find out, Zappata replied, though he already suspected the answer would be unsettling. The real examination began when they opened the engine cowlings. The left engine port side came first. As the panels swung away and the Allison V1710 was revealed, Zappata's engineering team fell silent. It wasn't just the size, though the 12-cylinder liquid-cooled V configuration was enormous by Italian standards. It wasn't even the obvious quality of the machining, though every component gleamed with precision that Italian factories, struggling with material shortages and Allied bombing, could no longer match. It was the turbocharger system. Zappata had read intelligence reports about American turbochargers. The concept wasn't new, using exhaust gases to spin a turbine that compressed intake air. allowing engines to maintain sea-level power at high altitude. German engineers had experimented with the technology. Italian engineers had drawn up proposals, but nobody, not the Germans, not the British, certainly not the Italians, had successfully integrated a turbocharger into a production fighter aircraft. The Americans had done it twice, one for each engine, and they were building hundreds of these aircraft every month. The turbocharger assembly sat behind and below each engine, connected by a complex network of exhaust ducting that snaked through the tailboom structure. The turbine wheel, when Zappata carefully examined it, was a masterpiece of metallurgy, a precision-forged component designed to spin at over 21,000 revolutions per minute, while exposed to exhaust gases exceeding 700 degrees Celsius. "What alloy is this?" Mancini asked, running his fingers over the turbine blades. Zappata shook his head slowly. "Nickel, perhaps, or something proprietary. Whatever it is, we don't have it. And even if we could acquire the material, we lack the precision casting capability to manufacture it." The implications were devastating. Each P-38 engine, with its turbocharger system, could produce approximately 1,125 horsepower in war emergency power. That's over 2,850 horsepower combined. For comparison, the Daimler-Benz DB605 engine powering the latest Machi C205V, Italy's most advanced fighter, produced 1,150 horsepower. One P-38 had nearly double the power of Italy's best single-engine fighter, but the numbers grew even more daunting. Zappata began calculating the engineering requirements. The Allison V1710 displaced 1,710 cubic inches, 28 liters. The precision needed to machine 12 cylinders, 12 pistons, connecting rods, a crankshaft capable of sustaining 3,000 RPM under combat loads. The supercharger, the turbocharger, the intercooler, the oil cooling system, the radiator, and the reduction gearing was staggering. He pulled out his notebook and started listing the components. His assistant watched, then asked the question they were both thinking. "Could we build this?" Zappata continued writing for several minutes before answering. "Build one, perhaps? With 6 months, unlimited resources, our best machinists, and perfect conditions. Could we build it reliably? No, build hundreds? Impossible. The cooling system alone was a revelation of American engineering sophistication. The Allison used a liquid cooling system with remote radiators mounted in the wing leading edges, a position that minimized drag while maximizing cooling efficiency. The radiators themselves were precision-manufactured cores with hundreds of tiny tubes, each brazed with exact tolerances to prevent leaks while maximizing heat transfer. Italian radiator technology lagged years behind. Their radiators were heavier, less efficient, and prone to combat damage. "The Americans have solved problems we didn't even know existed," Mancini observed, tracing the coolant lines with his finger. "They've solved problems we knew existed but couldn't afford to address," Zappata corrected. The counter-rotating propellers represented another layer of complexity. The left engine rotated clockwise, the right counterclockwise, eliminating the torque effect that plagued single-engine fighters. This required mirror-image reduction gearing, different propeller governors, and careful synchronization of the engines. Zappata examined the reduction gearing, a precise assembly that converted the engine's 3,000 RPM to approximately 1,400 RPM at the propeller shaft. The gears were hardened steel, precision cut with tolerances measured in thousandths of an inch. "We couldn't make these gears," his metallurgy specialist Domenico Russo said flatly. "Not with our current steel quality, not with our heat treatment capabilities. These gears need to transmit 1,500 horsepower without failing. Our gears would strip under half that load." As the examination continued, a disturbing pattern emerged that Zappata found more troubling than any single component. Every system on the P-38 was designed with redundancy, maintainability, and operational flexibility in mind. The electrical system used a 24-volt architecture with redundant generators, one per engine. If one generator failed, the other could power all essential systems. Italian fighters used 12-volt systems with a single generator. The hydraulic system, which powered the landing gear, flaps and dive brakes, included redundant pumps and multiple circuit breakers. Italian fighters often used mechanical systems or single-point hydraulic systems vulnerable to combat damage. The fuel system incorporated self-sealing fuel tanks, a technology Italy had only recently begun implementing with complex cross-feed capabilities that allowed fuel to be transferred between tanks or engines shut down for economy cruises. But it was the ammunition capacity that truly shocked the Italian engineers. Each P-38 carried a 20-meter Hispano cannon with 150 rounds and 4 Browning M250 caliber machine guns with 500 rounds each, all concentrated in the nose. Total firepower, 1 cannon and 2,000 rounds of heavy machine gun ammunition. The Meiji C-205V carried 2 12.7 machine guns with 400 rounds each and a 12mm cannon with 200 rounds. The P-38 had 3 times the ammunition capacity and significantly more hitting power. They built a flying battleship, Mancini said, examining the ammunition feed mechanisms. Look at these feed systems. They're designed to function under high-G maneuvers without jamming. These motors, he pointed to the electric ammunition boost motors, ensure positive feeding even when the pilot is pulling 6 Gs in a tight turn. Zappata was taking notes furiously but had stopped writing technical specifications. Instead, he was calculating production requirements. Each P-38 required approximately 50,000 individual parts. The engines alone contained over 6,000 components each. The electrical system included 8 miles of wiring. The hydraulic system required precision-machined valves and seals that Italian suppliers couldn't reliably produce. The aluminum airframe required alloys Italy was struggling to obtain due to material shortages and Allied blockades. He looked up at the Lightning sitting on the tarmac, and for the first time in his career, Filippo Zappata felt genuine despair. This wasn't just an enemy aircraft. It was evidence of an industrial revolution that had left Italy behind. That evening, Zappata sat in his office at Guidonia and began writing his report. The technical specifications filled 12 pages: measurements, component analyses, materials assessments, and performance calculations. But it was the final section marked Strategic Assessment that Zappata knew would be controversial. He wrote, "The Lockheed P-38. Lightning represents a level of aeronautical engineering sophistication that exceeds Italian manufacturing capabilities by a margin of approximately 5 to 7 years at our current rate of development. The engine powering Italy's most advanced fighter, the Meiji C-205V, produced 1,150 horsepower. One P-38 had nearly double the power of Italy's top single-engine fighter, but the disparity grew more evident. Zappata started calculating the engineering demands. The Allison V-1710 displaced 1,710 cubic inches, 28 liters. The precision required to machine 12 cylinders, 12 pistons, connecting rods, a crankshaft that could handle 3,000 RPM under combat loads, the supercharger, turbocharger, intercooler, oil cooling system, radiator and reduction gearing was immense. He pulled out his notebook and began listing the components. His assistant watched and then asked the question they both feared. Could we build this? Zappata continued writing for several minutes before responding. Build one, perhaps? With 6 months, unlimited resources, our best machinists and perfect conditions, could we build it reliably? No. Build hundreds? Impossible. The cooling system alone was a masterpiece of American engineering. The Allison system used liquid cooling with remote radiators mounted in the wing leading edges, minimizing drag while optimizing cooling efficiency. The radiators themselves were precision-manufactured cores with hundreds of tiny tubes, each brazed with exact tolerances to prevent leaks while maximizing heat transfer. Italian radiator technology lagged years behind. Their radiators were heavier, less efficient, and prone to damage in combat. "The Americans have solved problems we didn't even know existed," Mancini said, tracing the coolant lines with his finger. "They've solved problems we knew existed, but couldn't afford to address," Zappata replied. The counter-rotating propellers added another layer of complexity. The left engine rotated clockwise, the right counterclockwise, eliminating the torque effect that single-engine fighters faced. This required mirror-image reduction gearing, different propeller governors. In careful synchronization of the engines, Zappata examined the reduction gearing, a precise assembly that converted the engine's 3,000 RPM to approximately 1,400 RPM at the propeller shaft. The gears were hardened steel, precision-cut with tolerances measured in thousandths of an inch. "We couldn't make these gears," Domenico Russo, his metallurgy specialist, said flatly. "Not with our current steel quality or heat treatment capabilities. These gears need to transmit 1,500 horsepower without failing. Our gears would strip under half that load." As the examination continued, a troubling pattern emerged that Zappata found even more concerning than any individual component. Every system in the P-38 was designed for redundancy, maintainability, and operational flexibility. The electrical system used a 24-volt architecture with redundant generators, one for each engine. If one generator failed, the other could power all essential systems. Italian fighters used 12-volt systems with a single generator. The hydraulic system, which powered the landing gear, flaps, and dive brakes, included redundant pumps and multiple circuit breakers. Italian fighters often relied on mechanical systems or single-point hydraulic systems vulnerable to combat damage. The fuel system had self-sealing tanks, a technology Italy had only recently begun implementing, along with complex cross-feed capabilities, allowing fuel to be transferred between tanks or shut down to economize fuel. But it was the ammunition capacity that truly shocked the Italian engineers. Each P-38 carried a 20mm Hispano cannon with 150 rounds and 4 Browning M2 50-caliber machine guns with 500 rounds each, all concentrated in the nose. Total firepower, 1 cannon and 2,000 rounds of heavy machine gun ammunition. The Meiji C-205V carried 2 12.7mm machine guns with 400 rounds each and a 12mm cannon with 200 rounds. The P-38 had 3 times the ammunition capacity and far more hitting power. "They built a flying battleship," Mancini said, examining the ammunition feed systems. "Look at these feed systems. They're designed to function under high G maneuvers without jamming. These motors," he pointed to the electric ammunition boost motors, "ensured positive feeding even when the pilot was pulling 6 Gs in a tight turn." Zappata took notes furiously, but he stopped writing technical specifications. Instead, he began calculating production requirements. Each P-38 required roughly 50,000 individual parts. The engines alone contained over 6,000 components each. The electrical system included 8 miles of wiring. The hydraulic system required precision-machined valves and seals that Italian suppliers couldn't reliably produce. The aluminum airframe needed alloys Italy was struggling to acquire due to material shortages and Allied blockades. He looked up at the P-38 sitting on the tarmac and, for the first time in his career, Filippo Zappata felt genuine despair. This wasn't just an enemy aircraft. It was proof of an industrial revolution that had left Italy behind. That evening, Zappata sat in his office at Guidonia and began writing his report. The technical specifications filled 12 pages: measurements, component analyses, materials assessments, and performance calculations. But it was the final section, marked Strategic Assessment, that Zappata knew would be controversial. He wrote, "The Lockheed P-38. Lightning represents a level of aeronautical engineering sophistication that exceeds Italian manufacturing capabilities by a margin of approximately 5 to 7 years at our current rate of development, where Italian engines gasped for air. The German Bf-109G, with its DB-605 engine, lost considerable performance above 25,000 feet. The P-38, however, thrived in this environment. Its speed advantage allowed American pilots to choose when to engage and when to retreat. Italian fighters attempting to intercept could easily be outrun by simply pushing the throttles forward. The armament concentrated in the nose proved devastatingly effective in mock combat. Italian fighters with wing-mounted guns faced convergence issues. These guns were typically harmonized to converge at 300 meters, but were less effective at other ranges. The P-38's nose-mounted weapons had no such limitation. It was a point-and-shoot system. What disturbed Italian engineers most, however, was what they discovered when they began dismantling the components for detailed analysis. The build quality was extraordinary. The welds were flawless. The machining was precise. The materials were top-tier throughout. There were no shortcuts, no compromises, and no signs of resource constraints. An Italian engineer inspecting the engine noted, "Every component appears overbuilt to a safety margin we cannot afford." While Italian design maximized performance with minimal materials, American design achieved performance through superior materials and manufacturing. "We build to the edge of what's possible," Zappata mused. "They build with margins that assume some components will fail and the aircraft will still fly." This philosophy extended across the aircraft. The structural members were heavier than strictly necessary, offering durability and damage tolerance. The electrical system included more circuit breakers and redundancy than Italian engineers would have ever specified. The hydraulic lines included armor protection that added weight but significantly enhanced survivability. It was engineering from a nation with virtually unlimited resources, and it worked. The P-38's legendary toughness wasn't an accident. It was built in from the beginning. Zappata's report ascended through the chain of command. The technical sections were forwarded to Italian aircraft manufacturers, instructing them to identify relevant technologies for potential implementation. The strategic assessment reached the desk of Mauro Dell'Aria Reno Corso Fuggier, chief of the Italian Air Force. After reviewing it carefully, Fuggier filed it away. There was nothing to be done. Italy simply didn't have the industrial capacity to replicate American technology. German support was focused on their own programs. The best Italian engineers could hope for was to optimize existing designs and rely on pilot skill and tactical creativity to overcome the material disadvantages. It wouldn't be enough. Everyone knew it, but no one could say it publicly. On August 11, 1943, Tandy flew the captured Lightning in combat. Intelligence reported a formation of American B-24 Liberators returning from bombing Tandy. Tandy took off from Guidonia, climbed to altitude, and positioned himself for the attack. Using the Lightning's familiar silhouette to approach undetected, he opened fire on a lagging bomber. The concentrated firepower from the cannon and 4 machine guns shredded the Liberator. Tandy claimed the kill, possibly a B-24 named Bonnie Sue or Lady Evelyn, depending on conflicting records. It was a small victory. A captured American fighter flown by Italy's best test pilot had destroyed one American bomber. For propaganda purposes, it was useful. For strategic purposes, it was meaningless. The Lightning was grounded shortly after, without spare parts, maintenance manuals, or the logistic support necessary to keep American P-38's flying. The captured aircraft became a hangar queen. Tandy never flew it again. The war moved on. Italy surrendered in September 1943. The Lightning at Guidonia fell into German hands before being destroyed to prevent recapture. Zappata's report survived in the archives, a technical document marking the moment when Italian engineers fully realized the extent of American industrial might and found themselves unable to respond. After the war, when production figures were declassified, Zappata's estimates were found to be conservative. The United States produced over 10,000 P-38 Lightnings across all variants. Each one required two Allison V-1710 engines, meaning 20,000 engines just for the P-38 program. The Allison V-1710 was also used in the P-40, P-39 and P-63. Total production exceeded 70,000 engines. Italy's entire wartime production of aircraft engines across all types and manufacturers amounted to approximately 13,000 units. America produced 5 times that many of a single advanced engine type. The disparity extended to every category. The US produced over 300,000 aircraft during the war. Italy produced approximately 11,000. American aluminum production in 1943 alone surpassed Italy's total wartime output. American factory workers, many of whom were women who had never worked in manufacturing before, assembled complex aircraft with a precision that Italian craftsmen struggled to match. Years later, in the 1960s, an Italian aviation historian interviewed Filippo Zappata about his examination of the captured P-38. The engineer, now retired and reflective, spoke carefully about that June day in 1943. "I knew we would lose the war when I opened those engine cowlings," Zappata said, "not because of any single component, but because of what the entire aircraft represented. The Americans had built a fighter that required 50,000 parts, including 2 of the most complex engines in existence, and they were producing them in quantities we couldn't match with our simplest designs. When I calculated the man-hours, the materials, the precision machining, and the quality control required, it was clear we were fighting an industrial giant that had barely begun to mobilize. The P-38 wasn't their best fighter. It was just one of several advanced types they were producing simultaneously. While we struggled to build 100 fighters per month, they were building thousands, all of them as good or better than our best designs." "Did you ever fly in a P-38?" the historian asked. Zappata smiled. "No," he answered. "Tandy offered, but I declined. I'm an engineer, not a pilot, but I didn't need to fly it. The numbers told me everything. Power-to-weight ratio, wing loading, thrust available versus thrust required. The mathematics of flight performance are unforgiving. The P-38 had superior power, superior altitude performance, superior firepower, superior range, and superior systems. It was better, and there were thousands of them. The captured P-38G at Guidonia never saw extensive combat service. It flew a few test flights, participated in one combat mission, and then sat in a hangar as a technological curiosity, evidence of a war already lost. It was analyzed by engineers who understood the implications, but were powerless to change them. The story of the captured Lightning is ultimately one about industrial capacity and the mathematics of modern warfare. Italy entered World War II with skilled aircraft designers, talented pilots, and a proud aviation tradition, but they lacked the industrial infrastructure to compete with American mass production. They lacked the resources to develop advanced technologies like practical turbochargers. They lacked the materials to build with, American safety margins, and they lacked the time to close a gap that widened with each passing month. Filippo Zappata's report documented this reality in precise engineering terms. 2 Allison V-1710 engines producing 2,250 combined horsepower, turbochargers maintaining sea-level performance at 25,000 feet, counter-rotating propellers eliminating torque effects, concentrated nose armament with 2,000 rounds of ammunition, and systems integration and redundancy that prioritized operational effectiveness over weight savings. And behind it all, an industrial machine capable of producing these complex aircraft at rates that made Italian production seem insignificant. The captured P-38 sat on the tarmac at Guidonia for only a few months, but for the Italian engineers who examined it, who measured its components and calculated its implications, that aircraft represented a turning point, the moment when mathematical reality overwhelmed tactical optimism, and they understood that this war would be decided not by courage or skill, but by factories, resources, and industrial capacity. America had all three in abundance. Italy had none. The lightning was proof, and no amount of Italian engineering genius could change that fact.